Some people say that soon robots will take over every human task in a production line. This means all human interface will be eliminated and robots will automate the entire process. Robot operating system, artificial intelligence, and machine learning have made automation systems much more intelligent and applicable as modern solutions for existing automation systems, making them much more efficient. When automation is considered, Indo navigation is one of the most prominent solutions for a type of self-navigation robots. We have developed a bot which would follow commands and has the intelligence to move on its own to a given destination. The robot has the ability to recognize its location in space and map the entire factory floor area. Through the used algorithms, the robot know the shortest and the most efficient path to travel around the factory floor area. This bot is made as a requirement to move around PCBs around the factory premises at Vario Systems Private Limited. The robot structure consists of a main controller as well as a secondary controller for the wheels. All the outputs to the wheels as well as the inputs from the encoders are directly connected to this PCB, and all the outputs are sent out to the controller via the PCB. There is a slot for the motor driver, which in turn powers the wheels according to the instructions given by the controller. The basic architecture of the PCB is as follows. Here lies a buck converter, which is the LM2596, and then there are three protection diodes as well as a main diode which is larger to protect for any backward current from the motor driver. And at this place there is the motor driver, and over here the pins which connects the motor driver to the controller. And on this side there's a master switch as well as the inputs for the encoders, the encoder power which is 5 volts, as well as space for USB power output in case any other component should be powered by 5 volt USB power supply, as well as there's another port to output 5 volts in case more power is needed for the other sensor modules such as the IMU. This is the motor driver which is used for this robot. This is the TB6612 FNG motor driver. The reason for using this motor driver is a small size and the ability to process high currents. And also this motor driver provides a special pin called the standby pin, which can easily stop the motor in case of any errors. This is the RP LiDAR A1 module. The RP LiDAR A1 is a low-cost 360-degree 2D laser scanner module. It can perform 360-degree scans with a range of 6 meters. It can rotate at a maximum frequency of 10 Hz and generate 2000 samples per second. This is how the RP LiDAR functions. And the RP LiDAR works on 5 voltage power supply and has serial UART communication with the control module. The other module used for this project is the MPU 6050. This is a 3-axis gyroscope module. It uses I2C communication and the power supply is 3.3 volts. The main coprocessor used for this project is the Raspberry Pi Model 3B. It has a 1.4 GHz ARM Cortex processor with a RAM of 1 GB. The ROS platform is installed on this module. Indo-localization and mapping are the vital part of Indo-autonomous robot. This robot was implemented on the Robot Operating System platform. As the project is being implemented by the Robot Operating System, there is a need to create a robot model using ROS. The most important factor of this part is that all dimensions of this robot model should be in alignment with the hardware robot model. As an example, gaps between the sensor placement of the hardware robot model should be aligned with the sensor placement of the robot model that is being created by ROS. ROS provides packages that are capable of creating 3D robot models with high quality. A vital sub-package in the robot model meta package is the URDF, is known as Unified Robot Description Format, which is an XML file that represents the robot model. A URDF file can be used to define a robot model, sensors, and the working environment. It also includes an XML tag that works on modeling the robot. Link tags and join tag are some other essential tags of this package. Initially, the robot is moving around the Indo environment and collecting information of the static objects. The ROS provides Gmapping package to map the entire Indo flow. Gmapping map represents the environment as a 1 meter by 1 meter grid cells, which is essentially needed to estimate the navigation path. Mainly, two input nodes are used for Gmapping map, which are odometry of the robot and the laser scan details. Odometry details of the robot can be obtained by using rotary encoder values and MPU sensor readings. Lack of precision of these encoder readings can be eliminated by using a PID controller and an extended Kalman filter. As the mapping of the robot is conducted manually, it is necessary to provide a command to the robot. Another basic need for this procedure is to create keys to control the node that can be used to map the linear direction and angular direction while the robot is in motion. Movements and the speed of the robot can be mapped to the keys. When the particular key is pressed, its linear and angular velocities are mapped to the PWM of the motor using PID. When the robot starts to move, encoder reading provides a distance moved by each time interval. X and Y and theta can be obtained by using the known kinematic equations. However, encoder values measure inaccurate measurement when robot is moving non-linearly. This error is accumulating with the robot movement. The MPU 6050 sensor is used to measure raw, pitch and yaw of the robot due to encoder fails. Extended Kalman filter is used to merge IMU data and odometry data from the encoder readings, and this provides accurate odometry measurements of the robot when the robot is commanded to move. After mapping the environment, the map can be generated to server to use navigation algorithm. However, above map is to identify static objects in the environment, but dynamic objects can be appeared to robot's trajectory. Due to this issue, new path has to be decided using the Dijkstra algorithm in real time. Therefore, few configuration files have to be built to create local map to identify dynamic variations. Global Planner runs the algorithm which defines the shortest path from the robot to the given goal location. Ross gets the ability to identify the shortest path from the Dijkstra algorithm. Local Planner starts to run when the robot begins to move to the goal point. This package provides a controller, which is a kinematic trajectory, to make the robot connected to the global planner until it reaches the goal location. Along the way, the planner creates a function represented as a grid map. This function encodes the cost of traversing through the grid cells. The controller's job is to use this value function to determine the dx, dy, and d theta velocities to send to the robot. The importance of using this package is if there are any barrier in the pathway of the robot, it creates a new path by avoiding those barriers. This package uses an algorithm which was named the trajectory rollout and dynamic window approach. Adaptive Monte Carlo localization, which is also known as AMCL, is one of the advanced algorithms which provides for the ROS platform for localization. This algorithm is used to measure the location of the robot using particle filters. Basically, this measures the localization based on probabilistic distribution of multiple sensor values. Some particles are used to present the location of the robot, which uses a particle filter to track the pose of the robot against a known map. AMCL algorithm can be implemented by using ROS. This algorithm node should be subscribed to odometry details from the encoder values, laser scan, and map. In this configuration file, many attributes have to be defined. However, mainly few attributes have to be changed while others can remain as their default value. Initially, the particles can be seen much more spread out the robot, and once the robot starts moving to the endpoint, the particles cluster all together near the robot model. The importance of this algorithm is when a dynamic obstacle, such as a human, is detected in the factory floor premises. The LiDAR sensor can fail while the encoder readings are accurate. Also, there can be a case where encoder readings can fail due to slip, hence the LiDAR sensor provides accurate location measurement. Considering both these cases, the Monte Carlo algorithm can provide accurate location measurement. TensorFlow API provides many object detection models, which is included pre-trained neural network classifier to train for custom object detection. Faster RCCN classifier is used to detect custom objects in this project. The reason to apply this model is the accuracy of RCCN classifier is high compared to single shot detection classifier. Challenging part is to implement object detection systems in ROS node. ROS node provides CV Bridge library to interconnect with the ROS node and OpenCV images. Reason is for that ROS nodes restrict to subscribe images from USB camera as ROS messages. The CV bridge acts as a bridge to connect ROS messages and CV image. Hereafter, OpenCV function can apply to images from the USB camera. The ROS network was configured as follows. The development computer identifies where ROS master, which in this case the Raspberry Pi, is within its local network. The network configuration was done by finding out the IP address of the Raspberry Pi and the development computer. In the ROS network, the LiDAR and the Arduino is serially connected to the Raspberry Pi module. The Raspberry Pi and the development computer is serially connected over a Wi-Fi network. One of the problems that was encountered when configuring a robot is that the components of each hardware component changes each time the main controller board restarts. To overcome this problem, we used simple UDIV rules to define its static names on the ROS launch files. Since we are using the IMU for our robot position estimation, the IMU calibration process requires to tilt the IMU in different directions. Since our robot is bit large in size, this calibration process is helpful and should be done accurately before all other components are connected to the robot. It was implemented through a simple ROS launch file. In order to maintain the speed sent by the navigation stack, PID controller has to be tuned properly. The ROS simple GUI was implemented to tune the PID constant values. Since ROS mainly works on command line interface, it was essential to have a GUI in a separate place to monitor and control the robot. The Qt Creator was selected as the GUI development tool. The ROS master is connected to the Qt framework. The Qt framework connects to the genome terminal through the Q process. Once a successful connection is established, the GUI can be used to control the robot. The GUI consists of the following tabs: the ROS master tab, video camera tab, IMU data tab, teleoperation tab, configuration tab, and the help tab. In the right side, as you can see, there is a terminal to include simple commands to the genome terminal. In order to establish connection, you first have to go to the configuration table and enable the ROS master. Then you can go to the ROS master tab and click connect in order to establish a secure connection. If you want to include the IMU data, you can go to the configuration tab and enable IMU module. And then if you go to the IMU data tab and press start, you can see the IMU data flowing, and once you press the suspend button, it will pause the data flow. If you want to enable the video camera, similarly you can go to the configuration tab and click on enable video, and then go to the video camera tab and check the video input feed. In order to establish the controls for the robot, you can go to the teleoperation tab and select what kind of controller you will be using for the robot controls. There are several ways in this robot can be further improved. For example, there can be issues where laborers might not be able to use new technology. It is better if there is a system which works on singular voice commands so that any laborer can use it to interact with the robot. And also, a system can be implemented for the robot to autonomously load the payload so that no human interaction is further needed.